Another part of this topic is the trapezoidal rule. We will be using this to estimate the area under a curve. So trapezoidal rule is actually, if we go back to the area of a trapezium, which is a half multiplied by the sum of the lengths of parallel sides times the distance between them. So if we're more familiar with this type of trapezium, as we see, we have two parallel sides which represent the small a and the small b, and the distance between them in this case is the height. So it's the perpendicular between them is the height, and this is the formula that we normally use for calculating area of a trapezium. So using this, let's consider the curve given to us here, y equal f of x, and we have x equal to a. At x equal to a is the point A, at x equal to b, the point B, and we have AD equal to f of a, and BC is f of b. So if I need to apply the formula of finding the area under the trapezium that we have, let's draw first join CD, and now we have a trapezium ABCD. So if we apply the formula to us, the distance between the perpendicular distance between the two parallel lines is AB. So to us this is H. So therefore, if I say the area of a trapezium ABCD would be H over 2, which is in this case AB over 2 multiplied by the sum of the lengths of the two other opposite parallel lines, which is AD plus BC. And this is exactly what the area of a trapezium. So transferring this to other forms, area would be equal to a half. The length AB would be from here to there minus this bit, so it's actually B minus A, bracket, AD representing, as we said, f of A, and BC representing f of B. So this is actually will be leading us to finding the approximately the area under the curve y equal f of x. So this is what we call a trapezoidal rule, and the formula is used for only one application. So if we write it down, integration from a to b f of x dx is approximately equal to a half b minus a, brackets, f of a plus f of b. And this is what we call one application of a trapezoidal rule. Let's have a look at this example. We're supposed to find the exact area under the curve y equal x squared, which is a parabola between 0 and 2. And the next part is finding an approximate area using the trapezoidal rule. We just have to see the difference approximation in the error of finding using the two ways. Having a look how this would look like if we sketch it roughly. It's just a curve, and it's from x equals 0. So they want the area between 1 and 2. And we can make it look like a trapezium. Okay, so exact area is just a simple integration from 1 to 2 x squared dx, which is equal to x cubed over 2, and we are substituting 1 to 2. From that we get 8 over 3 minus a third after substituting, and on the calculator it gives you 7 over 3. That's the square units. So that's the exact area. Now if we use the second part, area of a trapezium, what we get a half b minus a bracket f of a plus f of b, using the rule of one application of trapezoidal rule. So it's a half b minus a, which is to us 2 minus 1, f of 1. We'll have to substitute f of 1, f of 2 in our function y equal x squared. So we end up with a half times f of 1 is 1 squared plus 2 squared, and all that gives us a half times 5, which is 2.5 square units. You see the difference here in the two. If you subtract that, 2.5 minus 2 1/3, this is actually 2 1/3. It gives you about a 6. So 1 over 6 is actually our error between the two areas. Now if we wanted our approximation to be much closer to the exact area, we will have to divide it into two equal subintervals, and then applying the trapezoidal rule to each subinterval. And that would be in the form of, if we look at our curve, we had 1 to 2, so we're going to divide it into two parts, of course equal parts, so the middle one will be 3 over 2. So we'll be using the trapezoidal rule to each subinterval. So we'll have to have area 1, area 2. So the total area will be area 1 plus area 2. Now, another thing we need to know is the width, which is the width of each subinterval. So in this case, if we have to, divide the interval into two parts, so the width would be for us 2 minus 1 over 2, so it's a half. So each width in this case is a half. Therefore, the area that we're looking for would be a half. The other half comes from the width of the interval. For the first one, area 1 will have f of 1 plus f of 3 over 2. That's the first one. Plus, again, a half times a half. F of, this time, 3 over 2 plus f of 2. Now we can fix this up together. So in this case, that's a quarter. That's a quarter. And as you notice, we have f of 3 over 2. It's repeated here, so we'll have 2f of 3 over 2. So the actual formula, the calculation will lead to a quarter as a common factor between them. So we have f of 1 plus 2 of f of 3 over 2 plus the last one, f of 2. Substituting in, you will end up with a quarter, f of 1, which is 1 squared, 2 times f of 3 over 2, 3 over 2 all squared, because we're still using the curve y equal x squared, plus f of 2, which is 2 squared. And this will come up to be a quarter, or 1 plus 2 times 9 over 4 plus 4. And we end up with, after all the calculation, 2.375 squared. units. As you see, we are getting closer and closer to the exact value the more subdivisions we subdivide under the curve, the area under the curve. So our first exact area was, in part 1 was 7/3, which is 2 1/3, and in the part 2 we had 2 1/2, and this one we have 2.375, so it's getting closer to the actual exact area. And the more and more subdivisions we get, the closer we get. Of course, the width of each subinterval has to be calculated by h equal b minus a over n. N represents the number of subdivisions that you are taking to actually find the width of each subinterval. And the formula will be then looking like this. So for this one, if I said I wanted to find the area under this curve, f of x, that would be from a to b. F of x dx would be approximately h over 2. F of a is the first, plus 2 times f of a plus h, plus 2 times f of a plus 2h, plus 2 times f of a plus 3h, plus the last one, f of b. So the more and more subdivisions you will end up with, you will definitely be closer to the approximate to the area, closer to the exact area under the curve. So for us, let's say if we are finding an approximation, for example, from 1 to 2x squared dx, the example that we were doing, using this time 10 equal subintervals, we would have to do a little bit more calculation according about the width of each interval. So we'll be writing, first of all, trying to find h, which is 2 minus 1 b minus a over this time 10, because n in this case is 10. So our width of each interval is 0.1. Therefore, the integration from 1 to 2 x squared dx will be approximately written this way. It will be 0.1 over 2, big parenthesis, f of 1 plus 2 f of 1.1. So we're adding h plus a, h plus 2a, plus 2 f of 1.2. It'll be much easier to write down all the coordinates before we actually start substituting. So if we said the width is 0.1, so we say 1, 1.1, 1.2, etc., all the way to 1.9 and a 2. So this is what we're supposed to substitute in all that. F of, we're up to 2 times f of 1.3 plus 2 f of 1.4 plus 2 times f of 1.5, 2 times f of 1.6 plus 2 times f of 1.7, 2 times f of 1.8. We're nearly there to f of 1.9 plus f of 2. Now, having the curve which is only parabola, which is f of x that we had is x squared, it would be quite easy to substitute in So the area approximately is 0.1 divided by 2, which is 0.05. And going back to f of 1, as I said, f of 1 in this case is 1 squared, 2 times 1.1 squared. Or we could make it easier, put a bracket here, and say 2 multiplied by everything else on the inside. So we have 2 bracket 1.1 squared, 1.2 squared, until we get to the end of it. 1.6 squared plus 1.8 squared, 1.9 squared, close the bracket, plus 2 squared. And this all can be done on the calculator, and the approximate area would be 2.335, using of course a calculator to calculate all that. And this is actually trapezoidal rule of the same curve, but using this time 10 equal subintervals.